Entropy is what we're talking about here. Entropy, yes, it's letting me write, good. So in the past, people have kind of introduced entropy, and we've talked about something else that sounds very similar to this, which is enthalpy, and we actually use both of these in this unit. So you've got to really kind of like make sure you know what you're talking about, which one's which, okay? So enthalpy was heat, okay? Entropy, there's different ways to describe it, like they said here. When I was kind of introduced to it, they always said entropy is disorder. So how much disorder do you have? So for example, my desk right now is somewhat ordered. By the end of the day, especially when I've been doing these quizzes, it's just a pile, okay, and just out of order. It takes a lot of energy for me to put back in to get it back into that ordered state, and it doesn't seem to take that much energy to get it reversed, and get it disordered. So that's one way that you can kind of think about this. The other way, and heat has a factor in that. So as you heat things up, generally the entropy increases, okay? Because the particles are going to be able to spread out more. And if they're spread out more, that leads to more disorder because there's more places for them to go, right? If they're spread out more versus if they are condensed into here. So less disorder in something like this versus more disorder in this, because this particle could be here, it could be here, it could be, it could be all over the place. Does that make sense? So they call these microstates. So the fact that this substance, whatever it is in this container, would have more chances of having more microstates or more places that it could be versus something like this. Okay, so less entropy, more entropy. So entropy is in joules per Kelvin. Now the problem is that this is joules per Kelvin. Guess what enthalpy was? It was kilojoules, okay, per Kelvin, something or other, okay? So the problem is that you're going to have to convert one or the other over, but you should be able to convert between kilojoules and joules easily. This conversion between these two things should be easy in your brain, right? Because you know that for every one of these, you've got 1,000 of these. Anything between kilo and the base unit, there's 1,000, okay? Between that, if we did millijoules, which we're not going to work in, but that would be another, that would be 100,000, okay? So you need to get used to being able to just kind of almost as a matter of, almost second nature to be able to flip between these things. Does that make sense? All right. So if we have these two particles here, okay, and that has separate sections, there's one way to have both particles on the left. There's one way to have them both on the right over here. And then there's another way to have one here and one over here. So it is more probable to have one particle on each side, which means that if we have a system with two particles in two sections, it's more likely that at any given time, those particles are going to be spread out. So what this is saying is, given the opportunity, gas particles will spread out as far and wide as they can go. Well, any particles, actually. I mean, if you think about like water, when you drop water onto something, right? It doesn't just stay like this. It spreads out into a puddle, okay? So it's going to spread out as far and wide as it can. So in an actual chemical system, like a beaker, balloon, something like that, that's going to contain numerous possible sections. Again, we call those things microstates. So when the particles or the energy in the system are more spread out into the microstates, we say that that has more disorder or entropy. If the particles or the energy in the system are less spread out, then it has less microstates, and we say that that is less entropy. So if you think of like solids, liquids, and gases, a solid is going to have fewer microstates because it's going to be contained within a certain volume. Okay. Liquids take the volume of their they spread out as much as they can. They still have a fixed volume, but they're going to spread out more. So if you had this solid and it turned into a liquid, it would just be a puddle at the bottom of this thing. Okay, it would have more microstates than being contained within this. Okay, and then gases, of course, are going to have more freedom. They're going to have even more microstates because they're going to spread out as far and wide as they can. They don't have a fixed volume. So they have even more entropy than a solid or a liquid. So if you place the same amount of gas into containers with different volumes at the same temp, the gas in the container with the larger volume will have the larger entropy because it's going to have more possible places for those gas particles to go. Are you following me? So if you had a container that was this big and you had, let's just do 5 gas molecules, okay, they're going to spread out. They're going to have more opportunity to spread out versus a container that is this big. 1, 2, 3, 4, 5. This particle right here could be anywhere in this voided space here. So there's more chances, more places for it to be than, say, this particle in this container. Yeah.
So the microstates doesn't change the volume, but the entropy does? Or does microstates change?
So the amount of microstates that are possible increases with increased volume. Because this guy right here, he could be anywhere within this container. So any of those places within that container is considered a microstate. Yeah.
So a greater entropy has more microstates?
Yep. So increased, and I would almost say increased microstates equals an increased entropy. Does that make sense? All right. So we can see where we have an increase or a decrease in entropy. We can compare the moles of gas on each side. And if the products have more moles of gas, then we'll say that the entropy is positive. So delta means change in. That's going to be positive. So for example, let's just take water here. We've got hydrogen gas. We have oxygen gas. And we're going to make water. Okay. Over here, how many moles of gas do I have total? 3. Over here, I have 2. So this has decreased entropy. So the entropy would have decreased here. If I reverse that equation, here I have now increased my moles on the product side. So what has happened to my entropy here? It is increased. Yes, we have gone from 2 moles of gas to 3. So our delta S here would be a positive value. We don't know necessarily what it is, but we know that it's positive. Likewise, if I go and I have, let's take, just take water again. If I have water here that is in the solid state and I melt it, have I gone through a chemical change here? Nope, no chemical change, just a phase change. All phase changes are physical changes. Okay. This will have increased in entropy. This will have a positive entropy as well because this liquid would have more microstates than this. So anytime you go from a solid to a liquid or a liquid to a gas, you're going to increase your entropy. It's going to be positive. So here is just kind of a summation of that. Decomposition reactions, we've gone from 1 mole to 2 moles. So that is going to be an increase in entropy. Anytime you increase temperature, the particles are going to be moving faster. You are increasing your entropy. Anytime you go and dissolve something into ions, or even just dissolve something that doesn't go in ions, so just molecules. Okay, so you take sugar and you dissolve that in liquid. You've now gone from a solid to a liquid, essentially, because those ions are able to move around within that liquid. That makes sense? I mean, kind of logically how that works. Again, any kind of endothermic phase change, which is a physical change, that is going to increase your entropy. If you increase the number of moles of gas, that's going to increase it. And then gas expansion, increasing your volume. And then, of course, the opposite of all of that. Okay? So this is what I was trying to talk about. Anytime you dissolve something, you're taking a solid and a liquid, and now you're dispersing that solid, those solid particles, or now ions, within that liquid. You're gonna increase your entropy. All right, good. All right, so here we're going from a gas to a solid. What's going to happen to my entropy? It will decrease. Yep. So we're going to have a decrease. It's going to be a negative value here. Okay. This will have kind of condensed. It'll gone into like fewer microstates. So we were spread out wide and far, and now we're contained within just a small volume. Okay. Looking at pressures here. So at lower pressures, what happens to the volume? Right. So increased volume equals decreased pressure. If your volume is bigger, then your entropy is going to go up. So the thing at the lower pressure will have a higher entropy. All right. Here we've got a solid and a solid. So solid and solid this plus CO2 gas. I don't quite follow. Okay, so this stuff is together. This is together in one container, and this is in another container. So this is separate. So which one will have more entropy? This guy or these? Yep, these two. Because first of all, you've got a gas there. So that just overwhelmingly brings that out. You've also got 1 mole of stuff versus 2 moles of stuff. So that changes it too. Okay. All right. Formation of ammonia is an exothermic process that is spontaneous, that occurs at low temperatures. Okay. So they want us to complete the reaction showing one of the nitrogen molecules reacting with hydrogen. So one of the nitrogens here is going to react with the hydrogen. So this is nitrogen. That's going to react with, it says, with hydrogen. It doesn't specify how much hydrogen, which is good because we're going to need a few of hydrogens. Okay, so one of my nitrogens is going to come together with 3 hydrogens. Boy, that's a sad looking picture, y'all. Sorry. It's as good as you're going to get. Well, I'll try to do a little bit better with this one. 1, 2, 3. It's a little better. They don't expect you to be art students for AP Chem, thank goodness. Which means that I need to consider my conservation of mass here. So I've got to make sure that I draw in all the rest of these. So I've got all my nitrogens accounted for now. I used 1, 2, 3 of these to make these guys. So then I would have 4 left over. So 1, 2, 3, 4. Okay. So I've completed A. A is done. Did the entropy of the system increase or decrease? Well, we went from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on this side. Over here we have 1, 2, 3, 4, 5, 6, 7, 8. So what happened to my entropy? Well, we went from 10 things over here to 8 things over here. So it should have decreased. Okay. Also, you can look at this equation that they provided us. Over here, we have how many moles of gas? 4. Over here, we have 2. So that's another way to kind of look at it and see what happened. But I've got fewer things over here than I have over here. So that's a decrease in entropy. Good before we get into math? All right, you ready? You ready? You ready? Got your calculators out? Ready to go? So this equation right here should look familiar to you. Why? Huh? Yes, this is the same way that we do enthalpy, except now we have S's instead of H's, okay? But it works exactly the same way. So if you did okay on that one, this one's not bad. Well, it's not going to be bad. Okay, just hang with me, okay? I know this was one of the ones that I was gone for when I took my personal days, fled off to be with the pelicans and herons and all that good stuff. All right.
For as much as you talk about it, I really think we should have a class trip. We're all in AP Chem.
Yeah.
Isn't your kid a pilot?
He is. He is indeed. Yeah. If you guys will charter
That's real.
if you guys will charter the plane that he flies, then we can talk about it.
Okay.
No, we just have to figure out how planes fly. Yeah.
The plane that he flies generally rents for about $20,000 an hour.
So we'll find
It only seats 8 people, so you're gonna have to figure who you're voting off the
I was
island.
gonna say, so everyone's gonna
Yeah, no, I got her 8.
Oh, am I part of it?
Are the rest of us just gonna take buses?
Yeah, like no, you gotta walk.
Not my problem.
That'd be good.
Wait,
Yeah,
yeah,
I
they
know.
only find
I was just saying, I'm like,
Yeah, you'll find a broken leg.
All right, now
I got 2 cars.
we need to kind of be careful with this term spontaneous, okay? I'm eventually going to, within the next few days, remove this word from your vocabulary, so don't get too comfortable saying it, okay? Because they don't really like it, but we need to use it for right now until I can get all the pieces in place for you, okay? So when we talk about something that has a positive entropy, we call that a spontaneous process, meaning that it's just going to happen. So for example, if I have a cube of ice sitting on the table here, what's going to happen with it? It's going to melt. That will just happen, right? There's nothing that we can really, other than cooling it down in here. But at room temperature, that's just going to occur, okay? So if we have a positive entropy, then that means that reaction is just going to happen. Okay, we don't have to intervene. We don't have to add extra energy in to make it happen. It's just going to go. Okay, at equilibrium, your delta S will be 0. And then if it's less than 0, it's not going to happen. Okay. So those are kind of some ground rules that we're going to establish, and we need to be able to calculate our delta S from an equation. So this is the equation that you used before, okay? Yep. So it's not bad though, okay? So your delta S is just coming from a chart here, okay? You do multiply it by the coefficients. You're going to take your products minus your reactants and go from there. Okay, so let's get started here. I always start on this side because it's products minus reactants. So I start over here because I think it's easier. Does that make sense? Okay. If you dig back into, and I don't know if I put it in there or not, but back in your unit 6 stuff, there was a chart that had delta S and did I is that your unit 6 stuff? Okay. Yeah. So in your unit 6 stuff, there was a chart that had these in it. If you, for your test, they will always give you these things right embedded into the test, so you don't have to memorize any of these at all. Okay. All right. So I'm going to start over here. I've got my NO2, so I'm going to come over here and I'm going to find my NO2. I have 4 of those. So 4 times 240.1 is 960.4. Okay, that is 4 NO2s right here. That's what I have calculated here. Okay. Then I'm going to take my 6 waters. And remember, you've got to be careful with these because in those charts, that big chart that I gave you back in Unit 6, this is different for the different states of matter. So make sure that you're careful that you match up whatever is in the equation with whatever is in the chart. Because you might have 2, they may list 2 of these in the chart, and one's solid, one's liquid, one's gas. So be careful to make sure that you're paying attention to those states of matter. That is where I have commonly made errors. Like it's a very common place for me to mess things up. What are you doing?
We doing right now?
I'm giving notes.
I know. I didn't have notes, and I was going to ask after class.
He's just reading.
We're going to leave this way if you want.
Happy Wednesday, Libby.
Every Wednesday with
There's a reason I come to school at 8 o'clock in the morning.
It's for this class.
I'm going to add these up. That's going to be my products.
Every little goal is a goal, okay?
Then I'm going to go over and I'm going to do the same thing for my reactants. So now I'm going to do my reactants. I'm going to do them over here. Okay. Because I'm going to take this minus whatever I get for this guy over here. Okay. So now I'm going to do 4 times 192.8. I'm going to do 7 times 205.2. And then, how did I get that? What in the world? Is that right?
That's what I got.
Okay.
I mean, I don't trust it.
So 771.2, 1436.2. Yeah, I just must have miswrote on there. Yeah, I got 0.6 on my things. I don't know what I did, but the rest of it's okay. All right. I knew that this didn't add up to a 0.6.
Well,
All right.
1436.4 for that.
1436. Oh, you got a 4 here?
Yeah.
So then that's where I did my error. This is supposed to be a 6. Okay. So that's where I screwed up, was writing that 2 down. We will fix that for next year. Okay. That adds up. All right. So then we go through and do this process and determine our delta S equals, I got negative 114.4. What are my units? Joules per moles times Kelvin. Okay. If I wanted to change this, and which I'm going to need to do in the next few days, to kilojoules per Kelvin, what would that value be?
Wait, 114?
Yep, 0.1144. Okay. So kind of get used to, in your mind, switching this over to these kilojoules. And all you have to do is shift that decimal 3 spots. It's not a complicated math process, despite what my first year chemistry students always want to make it out to be. All right, good, bad, ugly, happy? Yes.
When it's negative, does that mean it has more entropy or less?
No, it's less. And all of these are gases, right? We went from 11 moles over here to 10 moles over here. So that validates what this is. Yep.
Does that mean that you'll need to do something in order for it to
Yeah, well, there's another component to this, which is temperature. Okay. So just based on entropy right now, it's not going to happen just spontaneously. Something else is going to have to factor in, which we're going to get to. We're going to combine entropy and enthalpy together in something called Gibbs free energy. That's the delta G. Yes. Okay. And that is what determines if a reaction will occur or not without any kind of outside intervention. Okay. So there's a way if you end up having something that isn't favorable, a thermodynamically favorable reaction, you can add energy in to make it happen. So for example, your batteries, okay, when you're using your cell phone during the day, it's draining your battery. That is a spontaneous reaction. Okay. In order for that reaction to be reversed and your battery charged, what do you have to do? Put energy in it with electricity, right? You have to connect it to some sort of electrical source, probably the outlet. It's faster than draining it from your computer, which you're going to have to regenerate that power for. Okay. But that is your battery in your cell phone during the day is a thermodynamically favorable reaction. And that is why those batteries actually don't work when it's really cold. And they tell you not to leave it in your car because they're not going to work. Because at those low temperatures, it's not thermodynamically favorable. That's also why, so yeah, that you have to keep that in mind. Those batteries just don't work well at those temperatures.
What about if it gets really hot?
Well, that oftentimes will roach your electronics. So it's going to somehow mess with the electronics in there. So, all right. So I want you and your seat buddy to figure out the next answer. I'm going to put the answer up there, but I want you to figure out how to get it. Okay. So don't look up at the answer until you get it done. Anybody else not able to tell me that they didn't have a packet?